Section 19C is all about electric circuits, which we just started to mention at the last set of notes, a tiny bit. But circuits, that is the path that the electricity flows through so we can use whatever it is we're trying to use. And more about that as we go along. So let's get ready and begin Notes 19C, electric circuits. Here we go. What is a circuit? Well, there you see a diagram of a circuit. Now, take a look here. I don't know how well you can see the arrows on your screen, but the electricity comes out of the negative end of this battery. And again, you could plug things into a wall and get the same idea. Go through the device. Now, not every circuit has a switch. I'll emphasize that again in a moment. Goes through the conductive wire into the bulb. Could be something else, doesn't have to be a light bulb, but bulbs are easy to use in diagrams. And then the current continues through the wire back into the source and repeats. And we have a continuous loop, as you're about to see in the words. Here we go. A continuous path for current to flow. It is a loop, and the conductive electricity will continue around and around and around and around as long as the circuit isn't broken. So we could turn off the switch, move this over to here to off, or we can unplug the device or do anything that we can without breaking the circuit to turn off the electricity. See, in the diagram you have a closed switch here. That's in the on position, and you have an open switch here. So when the switches are on, we have what's called a closed switch where the wires connect so the electricity can flow across. We turn this off. You notice here that these switches disconnect, and that's going to stop the electricity, kind of like a drawbridge where all the drivers wait for the bridge to go back down again, and then the drivers can continue. As soon as that path is broken, though, electricity will stop. Three parts that every circuit has: source, path, and load. In this diagram, the battery here is the source. Now, we could have stuff plugged into the wall, so the outlet would be the source. And then, of course, the electricity has to come from the electric company. The path is the conductive wire, and the load is whatever we're using: light bulb, computer, TV, refrigerator, toaster, whatever it is we're using that uses electricity, and then back into the source. Even battery powered stuff like a calculator. And some even have a little solar panel. So the solar panel is your source. You have the battery that's still going to shove that electricity through. Many calculators have both. And then the display screen would be your load. Every circuit has a source, a path, and a load. Now, keep in mind something though. Not every circuit has a switch. I emphasize that for a reason. Some things will turn on as soon as we plug those in or install the battery. Others have a switch that we can use to turn on and off. Now, we mentioned this before, that voltage is a force that pushes electric current through the circuit. Remember that difference in electrical potential we mentioned last time. Voltage is a force. Remember Newton's second law of motion: force equals mass times acceleration. If there's no force to push those electrons, then there's no movement through the circuit. The stronger the voltage, the stronger the electric current, and mathematically, we get a larger current. Remember, I equals V over R. Ready? Now, don't have to copy anything on here, just look. And we'll have some assignments that will have us look at these diagrams. And it may not be drawn exactly the same way on every paper, but I mentioned the open switch and the closed switch just a moment ago. When the switch is closed, the electrons can continue to travel across, like when the drawbridge is down. When the switch is open, it's like the drawbridge is up, the drivers have to stop and wait. Now, electrons are a whole lot more patient than humans are. Electrons will sit there for days, weeks, months, even years until somebody turns on the switch. A fuse and a resistor we're going to talk about near the end of this set of notes. Batteries, you know what batteries are. Cells are kind of like batteries, a source of electricity. In the diagrams, the output device or the load may be a lamp, which we use either an X4 or kind of a light bulb type of shape. Ammeter, we don't get into a whole lot in this class, but that just measures how much electric current there are. Buzzers and voltmeters. Voltmeters measure how much electrical force or voltage there has. and I just put the source where I got the diagram from. And you see at the top, pages 458 and 459 have descriptions of these diagrams and drawings. Ready? Two types of circuits, and both are shown up here. We have a series circuit, and on the next page you'll see a parallel circuit. Now look at the Christmas lights on the bottom, especially older Christmas lights. This one here, not quite what I'm about to say, but let's just say this pink bulb no longer lights. Well, if that's the case, in a series circuit, none of these bulbs are going to light up. That's because the circuit will have been broken. There's only one path for the electrons to flow. Okay, so let's do this. Come over here. And let's say there's a break right there. Bam. Now the electrons, they get blocked right here. There's a break in that circuit, so the electrons can't get across to this other side. Therefore, none of these lights are going to light up. Now, even if the electricity goes into the first light bulb and there happens to be a break right there, do you think that first one will still light up? That answer is no. We may get a quick flash, but since the electricity can't continue to go around and around and around, none of these things are going to work. So in those older style Christmas lights, if this bulb was broken, you had to take out each bulb, put in a new one. Oh, that didn't work. Take that bulb back out, put the old one back in, take out the next old one, put in a new one, and so on. And there may be 100 light bulbs on that string, because that one won't work, that one won't work, and that one won't work, and it'll take a long time to find that broken bulb. If one load goes out, all the loads go out. So why do you think buildings, your kitchen, your house, don't have series circuits? If something in that house were to break down, electricity-wise, nothing in that house would work. So that's why there's a disadvantage to using a series circuit. Ready? In a parallel circuit, if this bulb here were to stop, what about these other two? Would those still work? Well, let's see. We have a source. We're going to plug in the circuit into the outlet here. The electricity can go through this first bulb just like that and back around. Some of the electricity will come through here and back around. And some of the electricity will come through that third bulb and back around. And remember, there has to be a continuous loop, in this case 3 different loops here. Now, what if we open up this switch right here? Would bulb 2 light up? That answer would be no. Since this switch is open, that part of the circuit is broken, this bulb is not lighting up. What about the other 2? Yes, those 2 would light up, because each bulb has its own closed path for the electricity to go through and back around into the outlet. Same idea here. The electricity comes here, goes into that first bulb, and can go around to the second, and can go around to the third, and on back, and make it in. So even if that first bulb is broken, and the filament is part of the circuit also, so if that filament blows, the bulb burns out, well, the electric current, let's do it this way now, the electric current would still have a chance to get around that first one and into the second one, and so on, and complete the loop. So in a parallel circuit, what we have are multiple paths for that electricity to travel through, and that's a benefit. Now if something goes out in the house, everything else will still work. One broken lamp bulb or burned out bulb where that filament just breaks, that won't affect anything else. So that's why we want to have parallel circuits, because in a parallel circuit, if one load goes out, everything else will still work as long as there's no other breakage in the connection. So parallel circuits are much more advantageous. Ready? Oh, you see a calculator up there. Ha ha, you know it's coming now. A watt. Remember back when we talked about simple machines and work? Okay, watt is power divided by time, measured in watts. Power, let me say that again. Power is work divided by time measured in watts. Well, electrical power is electrical energy or electrical work. The unit is still the joule, still divided by time. So let's remember what that meant. Power equals work divided by time, and it's the same thing in regards of electricity. A kilowatt, remember kilo, the K, that means 1,000 watts. All right? Now, a little common sense here. More power uses more energy. Well, let's think about that. If power equals work divided by time, we have that fraction. What happens if we use more energy? We get more power. Or we could also say, in order to increase power, we have to add more energy. And that may sound good until the electric bill comes. Power is voltage times current as well. Okay, so power, P equals VI. And remember, just like with F equals MA and that kind of equation there, if I increase the voltage, well, if I increase one of two numbers being multiplied, well, I'm definitely going to increase the power. If I increase either one of those two numbers being multiplied, I'm going to increase the power. Power equals voltage times current. P equals VI. And a little common sense here. Since that's a force, if we apply more force, then we're going to get more power, just like in mechanics. So there's one of the formulas we'll talk about and do some practice problems with. Power equals voltage times current. Ready? Okay, another equation. Now I mentioned until the bill comes. Well, you ever have your parents get on to you for leaving things turned on? Leave the TV on, leave the room and don't come back? Well, that's costing your parents money on the electric bill. So whenever we leave something turned on, we leave that thing using more electricity. And that's because current continues to flow through. Well, power is work divided by time. Reminder, P equals W over T. Power is capital P, work is capital W, time is lowercase t. Therefore, if I simply change work into energy because they're both measured in joules, watch what I get here now. Again, I'll write it more in fraction form that you're used to. Power equals energy divided by time. And if I do a simple manipulation, multiply both sides by t, well, this is what I get. Those cancel, I get E equals P times T, or energy is power times time. So if I use more voltage, then I'm going to use more power, which means I'm using more energy. And you know what? The electric company is going to charge us by the amount of energy that we use. And the electric company will charge us by what we call the kilowatt hour. So we use so many watts of power, we convert watts into kilowatts, and then multiply by how many hours we use the device, and that's how much we're going to pay on the bill. And then you add up all the devices that use electricity in the house for the entire month. Now you might understand why your parents may get on to you if you leave stuff turned on. Well, one day you're going to pay the bills. The cost is the energy times the price. And we'll have some practice problems that will deal with how much something may cost to use electricity. But there you go. Reminder, power equals work divided by time. Do some manipulations. Energy is power times time, and cost is energy times price. Ready? Now, short circuits, you ever heard of those? Okay. All right, let's say coach tells you to run some laps, and here's your track that you're supposed to run around the track, and you decide, you know what, coach isn't looking, so instead of coming all the way to the end, I'm going to cut across here, and I'm going to come over here, coach isn't looking, I'm going to cut across here, and it kind of looks like I made a band-aid right there. But your blue path, that's your shortcut that you're not supposed to take. You're cheating. Electrons tend to get a little lazy. Electrons have to keep going really fast for as long as we keep devices turned on. Well, look here. Let me try to make that a little bit easier to see. Right there. You see here, this little burned out piece of wire here actually has two wires touching each other. All right, consider you make this shortcut and now other people start to make the same shortcut, and pretty soon it gets crowded in here. Well, if too many electrons build up where they're not supposed to, remember they're carrying electrical energy, you see what could happen here. You have some sparks. You have some fires potentially. A short circuit is when the electrons find a shorter path, that's why it's called short circuits, with lower resistance. The shorter the path, the less resistance for those electrons. That's like you take the shortcut because it's less for you to have to run, and the track itself is your resistance. Well, if electrons get caught, and remember a continuous loop, those electrons continue to build and build and build, well, then you can have sparks and potentially fires. You might burn down your house, and that's not something we really want to happen. So your definition of a short circuit, it is a shortcut. Two parts of wire that aren't supposed to end up touching each other. And that may happen a lot when the insulation that may be in between the two wires gets stripped away somehow, and those two pieces of copper end up touching each other. The electrons will build up there because of that short path, and then all kinds of hazardous things can happen. Fires, sparks, breaking down. Those sparks could fly onto other things such as paper that may be nearby, and all kinds of bad things can happen. So if you notice a short circuit, get that repaired or replace that cord or wire, or you may end up replacing your house. Ready? So how can we be safe? Well, there are some things we can do. Again, if you notice a short circuit, get that cord repaired or even replaced. It's a little expensive to have a repair done, but it's a lot more expensive to replace your home. There are things called resistors that hinder the flow of electrons. You go to lunch, a few of you are let in at a time, and everyone else has to wait. A few of you then get let in, everyone else has to wait. Remember, we talked about that before with semiconductors. Resistors are just like semiconductors. They hinder the flow of electrons, slow down the electricity, because most things we use every day don't need as much as electricity as may surge through your circuits in your house. These are just a few things we'll find resistors. Your stove, light bulbs, speakers, these are devices that block electrical flow and let just the right amount in. And there may be a series, maybe one here, one here, one here, one here, and one here, to prevent overload, because overload can cause that insulation to melt and those wires that aren't supposed to end up touching, leading to the short circuits, leading to the sparks, leading to the fires. So use simple little devices called resistors in your circuits. Many of your electronics, we mentioned semiconductors before, those circuits may have some resistors in there because electronics don't need a whole lot of electricity. Ready? All right, we have pictures of a fuse, a good fuse and a broken fuse, and what's called the circuit breaker panel right here. Now, my father was a master electrician, and I kind of wish now that I had learned more from him than I did. He's gone, he can't help me anymore. But what is a fuse? Many older homes use a lot of fuses in here. This is a small case with a very thin piece of aluminum wire right here. When too much electricity goes through that wire, look what happens. That wire melts and we get an opening like that, and that breaks the circuit. It's annoying. These things are only a few cents, but you have to replace that fuse. Take the broken one out, put a new one in, everything's good. And as long as this problem doesn't keep happening, we're okay, because all fuses eventually will melt down, just like all light bulbs eventually burn out. But if we have the same spot where you keep putting in new fuses, keep breaking that fuse, well, then you have a problem. You need a professional to get fixed. These things will prevent overload. Again, it's annoying to have to replace these things, but it's a lot more annoying to have to replace your house. Circuit breakers, you'll find one in every home that's been built within the last few decades. I just had mine redone last year, I believe, if I remember correctly. And right here, I don't know how well you can see, but these are switches here. And different circuits go through these circuit breaker switches right here. These are another safety device that help prevent overload. If too much electricity goes through, maybe this says dining room, goes through the dining room, then this switch will trip, which means turn off. It's annoying. Go out there, turn that thing back on, and all is good. But if the same switches, same breakers keep tripping and turning off, there's a much more serious problem that you need professional attention on. So these are just a few ways to practice electricity safety. Electricity can be very, very dangerous if not handled properly. Ready? Now, even newer homes have outlets, especially those maybe in the bathroom or the kitchen near the sinks, have buttons that we can push. These buttons act like tiny little circuit breakers that will trip if water gets too close or too much electricity near water gets in there. A GIF, a ground fault interrupter, in some of the outlets right here. There's a button to test to make sure everything's good. There's a button to reset. If this outlet stops, usually just hit that reset button and all is good. But once again, if this outlet keeps on stopping, then there's a more serious problem that needs repair. They're kind of like tiny little built-in circuit breakers for just that one outlet. They can be really nice because all I have to do is press that button. Of course, I don't want to press it with my finger, get something insulative, okay, that doesn't conduct electricity, and push on that. So you have test and reset buttons. You'll find these much more often in newer homes near water, such as sinks and faucets. Okay. Reset these when tripped, but again, if the problem keeps happening, get that looked at by a trained electrician. Ready? There you go. Charge ahead for an electrifying experience. We'll see you later.